scientists find how life evolved on Earth and probably on Mars. If life emerged on Earth via this simple path, it also likely emerged on Mars. This makes it even more important to seek life on Mars as soon as possible. RNA, an analog of DNA that is likely the oldest genetic material for life on the planet, spontaneously forms on basalt lava glass, researchers at the Foundation for Applied Molecular Evolution have announced. According to researchers, such glass was common on Earth 4.35 billion years ago. Today, remnants of such ancient basalts are still found on Mars. However, it cannot entirely explain how life originated on Earth precisely because of the complexity of this chemistry. This study, on the other hand, takes a simpler approach. Research led by Elisa Biondi shows that when nucleoside triphosphates percolate through basaltic glass, they form long RNA molecules, measuring between 100 and 200 nucleotides in length. Basaltic glass was everywhere on Earth at the time, commented Stephen Mogesis, an Earth scientist involved in the study. For several hundred million years after the Moon formed, frequent impacts coupled with abundant volcanism on the young planet formed molten basaltic lava, the source of the basalt glass. Impacts also evaporated water to give dry land, providing aquifers where RNA could have formed. As a result of these impact events, nickel also was released, which is demonstrated to give nucleoside triphosphates from nucleosides, and activated phosphates also found in lava glass. The formation of those triphosphates is controlled by borate, as in borax, aka sodium tetraborate. In addition to forming glass, metal iron nickel cores and the impactors temporarily reduced the atmosphere. The genetic information stored in RNA bases is formed in such an atmosphere. It was previously demonstrated that nucleotides are formed by direct reactions between the ribose phosphate and RNA bases. On the other hand, these same rocks resolve the other paradoxes linked to the creation of RNA in a way that leads from simple organic molecules to RNA itself. Borates, for example, are responsible for forming ribose, the R in RNA, Benner explained. In the atmosphere above primitive Earth, it is not possible for simple carbohydrates to form. Instead, volcanic sulfur dioxide stabilize the organic minerals and rain to the surface as reservoirs. Hence, this work completes a pathway that creates RNA from small organic molecules that would probably have been present during Earth's early history. As a result of one geological model, we get RNA molecules long enough to support Darwinian evolution. But researchers reveal that several questions remain unanswered. It remains unclear how the building blocks of RNA can all have the same general shape, a relationship called homochirality. Likewise, Benner explained that the nucleotide linkages in the material synthesized on basaltic glass can vary. This announcement is relevant to Mars since those same minerals, glasses, and impacts were also found there in ancient times. Martian rocks, however, have not been buried by continental drift and plate tectonics, as most rocks on Earth older than 4 billion years have. These ancient rocks still exist on Mars today. The research is noteworthy because recent missions have discovered all the necessary rocks on the red planet, including borate. If life emerged on Earth via this simple path, it also likely emerged on Mars, Benner commented. This makes it even more important to seek life on Mars as soon as possible. Furthermore, if life on Earth emerged in this way, and also on Mars, could it have also emerged on distant moons in our solar system, and exoplanets in nearby star systems?